Hello everybody, I am Horacio Gonzalez and we are here for a short introduction to Kubernetes operators. Why operators? Because operating Kubernetes, it isn't as easy as it could be. I mean, yeah, it's wonderful. With Kubernetes, you define your desired state. You declare what infrastructure do you want to be deployed. You give your YAML manifest files to Kubernetes, and Kubernetes is going to generate all those Kubernetes objects, the pods, the deployments, the services, the ingress, the load balancer, replica set, blah, blah, blah. And it works. It works very well for sample deployments. But what about something not so sample? For example, you are going to deploy a distributed database, I don't know, any kind of distributed systems inside your Kubernetes with lots and lots of different elements. Yeah, you are going to have lots of ingress services, deployment, pod, replica set, stateful set, persistent volumes, all that. If you are going to deploy this kind of architecture, trying to do it by hand is complicated, and trying to maintain it is even more complicated. How do you do things like upgrading a version? You have to individually upgrade versions of lots of individual items. That's why for complex development, it's nice to use some kind of package manager like Helm, for example. With Helm, you are going to build a Helm chart with all the different elements you want to put in your Kubernetes, and you are going to parameterize that with variables, and you deploy, upgrade, rollback, share it with only one sample command, and you are sure that the versions are always coherent, that you don't forget any other single YAML file, etc. It's great. But when you compare it with the normal task of a human operator, Helm only does the most basic ones, installing and upgrading. A human operator is going to do more things in the day-to-day work on the application or the infrastructure, installing, upgrading, life cycle of the application, inside. It means getting inputs from logs, metrics, traces, and trying to verify that the system works well and optimize it, and autopiloting, scripting things like adding new instance if needed, removing instance when not needed, and all that. All those tasks are routinary tasks for human operator. They take time. They don't have any big added value for the human operator. So in Kubernetes, we are in an automation philosophy. We want to automate at much as possible. So why don't try to build a Kubernetes component that will automate all these routinary tasks of the human operator, installing, upgrading, lifecycle, insight, and autopilot. How if we try to build a Kubernetes operator that is going to mimic the behavior of the human one? That's the idea behind Kubernetes operators. In order to build them, we leverage on two Kubernetes concepts. The first one are controllers. Controllers are control loops. They see your desired state, your YAML files, your Helm charts, and the current state, the real items deployed in your cluster. And if there are something different, they try to put the current state as near as possible to the desired state. In fact, it's a reconcile loop. It's going to observe, then it's going to see the difference between the two states and act on the current state to do it, to make it nearer to the desired state, and again, again, and again. The custom resource definition are another core Kubernetes concept. It is at the heart of the modularity of Kubernetes. You can extend Kubernetes API with new objects, and these custom resources are defined in custom resources definition, CRD. So with CRD, you can extend Kubernetes and you can define things that Kubernetes doesn't know before. For example, you can define, hey, I am going to define a node pool to manage a pool of Kubernetes nodes. Or I can define a new kind of load balancer. Or I can define a Harbor private registry. You define your new resources, and then you can pilot them from the Kubernetes API. And the Kubernetes operators take these two concepts, controllers and custom resources, in order to try to encode the human operator knowledge and generating a Kubernetes operator. For example, a human operator works day to day on some PostgreSQL or Redis database on your cluster. There are some tasks that are needed to do, for example, program scheduling backups or adding new instance to the cluster or sharding or resharding, rebalancing. All these kind of tasks are routinary for the human operator. Hey, in order to do a backup, I need maybe to stop the writing in the database, then launching the backup, then putting back the writes on, or in order to add a new instance, I need to do that, that, that. The idea is we are going to try to encode this task list into CRD and controllers. The idea is, for example, in order to do the backup, we need maybe an CRD for the database cluster and another maybe for the instance, and we need a controller that see if it is the right time for the backup, and then if it is the right time, it is going to use the CRD to stop writing and launch the backup, and then put the writing back on, or for adding a new instance to the cluster, it's going to do all the operation needed in order to add the new instance. So we encapsulate the business logic, the human knowledge into CRD and controllers in order to allow Kubernetes to do all these day-to-day tasks without the human operator intervention. And we do that creating the custom resource definition and the controllers and encoding the knowledge of the operator in them. Operators can be really smart or really basic. In fact, there is a whole capability model that is modeled in the 5-level tasks that we defined for the human operator, from basic install to autopilot. So when you see a Kubernetes operator, by seeing where it is in the capability model, you can see what kind of functionality it's going to have, from the most basic one that is almost like a Helm chart, installing, maybe upgrading, to the smartest operator that is able almost to do everything day to day on the infrastructure for yourself. So how are we using the operators in OVHcloud? We use them a lot, and we develop our own operators to help us in our day-to-day operation in our managed Kubernetes. We have, for example, a Harbor operator that we have given to the Harbor community in order to manage our private registry. We have a node pool operator in order to create and manage node pools and nodes, Kubernetes nodes inside Kubernetes using a CRD. We have a load balancer operator in order to pilot our IP load balancer. So for us, operators are a keystone in the operation of Kubernetes at a scale. And that's all for me. Thank you very much.
Hello there, I'm Pierre Peronnet from OVHcloud. I'm a member of the team which develop and maintain a Kubernetes product at OVH. I work on the open source Harbor operator since a year. First release was in the end of 2019. This operator is able to deploy the full Harbor stack. For your information, Harbor is an open source registry that secures artifacts with policies and role-based access control. It ensures images are scanned and free from vulnerabilities, and also signs images as trusted. The big part of this operator is to deploy all applications in the right order. Each of them are owned by a customer resource definition. So the operator has basically 7 CRD. The operator should take care of the configuration. Some of it must be hidden, some others must be shared across Kubernetes resources. It also should handle many different cases, since all resources can have many states. This leads to a complex engine which deploys Kubernetes resources. In order to the engine to smoothly deploy the full stack, it iteratively checks statuses of every dependencies before reconciling the resource. So in the code base, the dependency between every Kubernetes resources is managed by an oriented graph. So my point is how to be confident about what my own operator is actually doing inside my cluster. My first advice is probably obvious: observability. First of all, logs. Defining the right level of logs and pertinent fields are necessary to dig in operator actions and find out what is done. The second one is metrics. Basically, in case of huge number of requests, or if there is many reconciliation events that must be retried later, metrics are required. In one hand, to adapt infrastructure so it fits the load. In the other hand, to fix the operator to be more or less aggressive with the reconciliation rate limit. My second advice is about statuses. Do not only print error in logs. Try as much as possible to push error in Kubernetes resources. So anyone debugging resources will find information through kubectl commands. Moreover, any operator can use this status field to find the exact error and try to fix the issue automatically. Let's imagine that the volume storing Helm chart cannot be mounted. The error will be raised in the Chart Museum custom resource with some kind of invalid volume error. So any autohealing operator can fetch this error and take actions to repair it. The last but not least advice: describe as much as possible the resource that will be deployed. So CRD should be strongly typed. Any data or configuration should come from one or more Kubernetes resource. So you will have the power of Kubernetes to help you debug and manipulate configuration. With a well-defined API, site reliability engineers will be confident about configuration. If Kubernetes accepts the resource, it should be handled by the operator. Complex values can be validated thanks to webhook, so you have no excuse here. Customer resource definitions are hopefully versions, and Kubernetes is able to convert resources from one version to another one. Obviously, there is a downside with that. Development iterations are slow. Once new API is released, conversion methods must be implemented, and the new API must be requalified. But don't be afraid, all structures can still be used in new models, so the qualification process will be fast. In the Harbor operator project, I also added Jaeger, and I plan to add Sentry integration. Debugging this project is pretty easy, since actions taken by the operator are almost crystal clear. Thank you all for watching. Goodbye.